Hi, we're going to start on chapter 5, which is another chapter on bonding. We're going to go a little more in depth and look at bonding theories that are a little more correct than Lewis structures. Lewis structures are easy and VSEPR geometries, but they don't always give you the right answer. So we're going to look a little bit deeper. So first I want to introduce you to someone. Oh, he decided to leave. That was Grizzly. He likes to sit with me when I record, but he decided to get up. So we will just get started. Okay, so advanced theories of bonding. We're going to talk about valence bond theory, and a part of valence bond theory is the idea of hybrid atomic orbitals. We're going to talk about multiple bonds. We've already talked about multiple bonds in Lewis structures, but now we'll think a little bit deeper about where those electrons are. And then the next theory will be molecular orbital theory, which also has the concept of multiple bonds. So multiple bonds is a concept that you'll see in Lewis structures, valence bond theory, and molecular orbital theory. So the number one thing to think about as you compare this to Lewis structures thought of the electrons as dots. So we put them in as dots, but we did a whole chapter to understand that electrons aren't just particles, they have a wave nature. And so when we think about where you find electrons, we want to think about orbitals and probabilities rather than dots. So that's really what these two theories will add. This is just a picture to show you one time when Lewis structures and valence bond theory don't work, and that's for oxygen. When you look at the structure of oxygen, we've drawn it before. So oxygen you draw as a diatomic molecule, has two bonds, and each of those oxygen atoms then have two lone pairs. And in reality, oxygen is paramagnetic, which this picture is trying to show you. If you put it in a magnetic field, the magnetic field interacts with it because it has unpaired electrons. And you can't explain that with either Lewis or valence bond. So we have to go on to think about molecular orbital theory to discover why oxygen has unpaired electrons. That's just one of the times when molecular orbital theory, the most accurate theory, is needed. So valence bond theory, it describes the formation of covalent bonds in terms of atomic orbital overlap, and it gives examples of sigma and pi bonds. So the idea is that the more two orbitals can overlap in between the nuclei, the more probability that you'll find the electrons there, and therefore the stronger bond. So Linus Pauling and other of his collaborators in the 1930s developed valence bond theory for covalent bonds. He said that electrons reside in orbitals. So when you make a molecule, just like in an atom, the electrons are in orbitals and you can't know exactly where they are. Covalent bonds form when electrons are shared by the overlapping of singly occupied orbitals. So we'll look at examples of that. Electrons in these overlapping orbitals must have opposite spin. So if we think about the H2 molecule and HF, well, when we think about H2, I thought it was going to give some pictures. These slides don't have very many good pictures. So when you think about the H2 molecule, each of those hydrogens would have an electron in a 1s orbital, and therefore they're unpaired. And if you squish those two atoms together so that those s orbitals can overlap, you'd get a high probability of finding those two electrons in between the two nuclei. And that's what valence bond theory would tell you how the bond forms. So with HF, it's slightly different. Hydrogen has a 1s1, but fluorine has a 2p5. And so one of fluorine's p orbitals is unfilled. So if you have that p orbital on the bond axis, so the two lobes located along the bond axis, and it overlaps with the 1s orbital on hydrogen, you could also form a bond. And so that maximum overlap in between the two nuclei is what valence bond theory would say creates the bond. So to form a covalent bond, an atom must have unpaired electrons. That makes sense because if two orbitals are going to overlap, you need one electron in each, and then that new orbital forming the bond will have two electrons, which is the most any orbital can have. So the number of bonds formed by an atom is determined by the number of unpaired electrons. And this theory works well for explaining the bonding in diatomic molecules with only single bonds. This theory also works well for explaining the lack of bonding experienced by the noble gases. So if you think about a noble gas, it doesn't have any unpaired electrons. Therefore, it's not going to be able to overlap in any way and form a bond with some other atom. So valence bond theory must be modified to explain the covalent bond formed in other molecules. So if we look at these three molecules, it's going to introduce the idea of hybrid orbitals. So this just shows you that as those two hydrogen atoms get closer together, at the bottom of the well, where the molecule's length of its bond is its equilibrium bond length, you see that there's a huge overlap between those 1s orbitals. And so there's a high probability of finding the electrons between the nuclei, and that's what forms the bond. Whereas if you're at greater distances, the two atoms are so far apart that the orbitals can't even overlap. And if you try to squish it shorter on the left-hand side, the nuclei start seeing each other. So this shows you the idea of the maximum overlap. So if you have two p orbitals, the red and the blue just represents that the sign on those functions, one is positive and one is negative. So in order to get constructive interference, you need to overlap two orbitals that have the same color. That means you have two negative or two positive. If you were to overlap a blue lobe with a red lobe, they'd cancel because this function has the same size, but it's positive on one and negative on the other, so there'd be destructive interference. So in A, they're showing you a bond that could be formed from a p orbital on two atoms overlapping head on head. Whereas in B, if you notice, that's not going to form much of a bond because there's very little overlap if they're not head on head. This is a similar picture. This is showing you the idea of sigma bonds. So A would be our example of the hydrogen molecule, where each of the electrons on the hydrogens are in 1s orbitals. So when they overlap, you form a sigma bond. And then in B, similar idea, you can have a 1s orbital or any s orbital on one atom and a p orbital on the other, and they can overlap and form a bond if they're both the blue regions. So they both will then form constructive interference. And in C, you could also have two p orbitals, both on the bond axis. As long as their colored lobes are the same pointing at each other, you'll also get a bond. Each of these are called sigma bonds because if you cut it across the bond axis and then look at it, you'll see a circle, and that makes it a sigma bond. This is a picture of how a pi bond is formed. So if you have p orbitals on each of those nuclei, so the black dots are the nuclei, and if you have unpaired electrons in p orbitals on each of those, if you squish them together sideways, on top and on bottom, they're the same color, so they're going to overlap to create electron density and probability of finding the electron in between the nuclei, slightly above and below the bond axis, but still between the nuclei. When that happens, if you were to cut it across the bond axis and look down at one of the nuclei, you'd see a red lobe on the top and a blue lobe on the bottom. So that's not circular. So this we'll call a pi bond. So if we look at this, you have a sigma bond in HCl. The bonding is going to be exactly the same as it was with HF. The chlorine has an unpaired electron in a p orbital, so it can hit head on with the s orbital on hydrogen, giving you a sigma bond. Always multiple bonds. The first one is sigma and everything else is pi. And so we'll understand that a little bit better here in a second, why that's true. So this is an example. If you were to count the number of sigma bonds, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So every single bond and every first bond of a multiple bond is a sigma bond. So we have 9, but then we have 2 double bonds. So that second bond in each of those is a pi bond. So this is just showing you a picture, and I think it's one of the examples in the text where you're supposed to identify what kind of bond would form. So in A, you're going to get a pi bond. In B, you're going to get a sigma bond. And in C, you're going to get a sigma bond. So sometimes you can't explain the geometry or the number of bonds unless you do some mathematical operations with your functions, which is totally fine. It would be nice if we could do the calculus so you could see where these orbitals come from. If you take higher level physical chemistry, or if you take a quantum mechanics course in physics or modern physics, which includes quantum mechanics, you'll get to see the actual math, and this will make more sense. But hybrid orbitals are a theory that explain the concept of, or help us understand and explain the true geometries of molecules. So our objectives will be to understand these, and then also to think about which hybrid orbitals are associated with different geometries. This is exactly, I guess it went backwards. So hybrid orbitals, bonding in other molecules is best explained with hybrid orbitals. So when you have diatomics, you don't need hybrid orbitals, but most of the time when you have molecules with 3 or more atoms, you're not going to be able to explain the geometry unless you make hybrid orbitals. So keep in mind when you're working with hybrid orbitals that the number of hybrid orbitals formed always equals the number of atomic orbitals that are combined. So as we go through and think about this process, that will make more sense. So when we look at this picture, let's see what it says. Oxygen. Oh, this is to form water. So if we were, it doesn't actually say that, but that's the water molecule, because they're saying that it's oxygen in the middle and that then you have 2 hydrogen atoms. So if you look at oxygen's electron configuration, it is the valence shell is a 3s2, 2p2, and 2p2, no, 2p4. And so you have 2 p orbitals, each with 1 electron. But the problem is that when you look at the angles with those 2 p orbitals, they're 90 degrees apart. So that would make the angle in water 90 degrees, and it's more like 108 degrees. So we have to think about why that's true. So a water molecule has 4 regions of electron density. It has 2 lone pairs on the oxygens and 2 bonds. And so Vesper would predict that it's tetrahedral. And 2 of those hybrid orbitals on oxygen contain lone pairs. So we're going to talk about how you can make hybrid orbitals in order to describe the geometry. So this is going in a very strange order. So 2 atomic orbitals can hybridize to produce 2 hybrid orbitals. So if we take an s orbital and a p orbital, then we'll make 2 sp hybrid orbitals. And when we think about these, so you have an s orbital and a p orbital on the right. And if you had a single electron in each of those, you wouldn't really know what the geometry was. But if we add those together, we'll see that we'll form 2 new hybrid orbitals, which are called SPs. They're the yellow ones on the top. One's pointed positive and one's pointed negative. And so if you were to form bonds with those 2 hybrid orbitals, the bonds would be 180 degrees apart, which is consistent with what Vesper would say. If you have a central atom and 2 bonds to it, you'd have 180 degree angles. So sp hybrid orbitals occur when a central atom is surrounded by 2 regions of electron density. And yeah. Okay, so when you think about beryllium, beryllium's electron configuration is a 2s2, so it has 2 electrons in its valence shell. The p subshell is completely empty, so you have one pair of electrons in an orbital, and they're paired, so you wouldn't be able to form any bonds unless you thought about a way to change those orbitals. So to think about how they hybridize is you take one of the electrons in the s orbital and you excite it to a p orbital, and then the other 2 p orbitals are left alone, so they're the same energy when you go from left to right. But when you add together that s orbital and that p orbital, then you get 2 new orbitals called sp hybrid orbitals. They're slightly lower in energy than the p, slightly higher in energy than the s. But the important thing is now you have 2 orbitals which are 180 degrees apart, and they each have 1 electron in them. So when you think about how they can form bonds with chlorine, each of those sp hybrid orbitals can now overlap with a 3p orbital on chlorine to form a sigma bond on either side of the beryllium. So another kind of hybrid orbital is an sp2, and we'll see this is going to be the shape or the orientation of orbitals that we need when we know we have 120 degree angles. So 3 atomic orbitals can hybridize to produce 3 hybrid orbitals. So if you take 1 s and 2 p's, you'll get 3 sp2 hybrid orbitals. They occur when a central atom is surrounded by 3 regions of electron density. And if you remember from VSEPR, if you have 3 regions of electron density around an atom, the best geometry is going to be 120 degree trigonal planar. So how that happens is mathematically you take the functions on the left, you add them together, and what you get are 3 new orbitals pointing 120 degrees apart, and they're all equivalent. So this is what a set of 3 sp hybrid orbitals would look like. And so for something like boron hydride, boron is 1 further to the right, so it has a 2s2, 2p1, and so if you take, so this shows you the electron configuration it starts with. It would appear like boron can only form 1 bond because it only has 1 electron in its valence shell that's not paired. But if you take that p orbital along with another p orbital so that the s orbit electrons can unpair, and you add those 3 together, you get 3 sp2 hybrid orbitals, and then you still have 1 2p orbital that's not hybridized. So when we look at each of these would take sp2 hybrids, because the nitrogen has the lone pair, the single bond, and then all of those electron in the double bond want to go in the same direction. So you have 3 pairs of electron density. They all want to go as far apart as possible, so they want to be 120. So when you think about it, the nitrogen will have a lone pair in one of its sp2 hybrid orbitals. It will form a single bond with chlorine with another one of them, and the first bond in the double bond to the oxygen will be formed with one of them. So the carbon in the middle of the next atom, which is formaldehyde, that will also need 3 regions. So it doesn't have to be a lone pair and doesn't have to be single and double bonds. So on the carbon in the central molecule here, formaldehyde, carbon needs 3 regions for electrons to keep them as far apart as possible. So it's going to have sp2 hybrids. And then each of the carbons in ethene, which is the molecule to the far right, same situation. You want the bond in electrons to hydrogens to be as far apart as possible. And then you want each of those pairs to be as far apart as possible from the double bond. So you're going to have sp2 hybrid orbitals on ethene. So then the last kind of hybrid, well, we're going to also talk about some d hybrid orbitals. So this is the last s and p hybrid orbital set. So you have 4 atomic orbitals, which can hybridize to form 4 hybrid orbitals. You take 1 s and you take all 3 of the p orbitals, and you're going to form sp3 hybrid orbitals, 4 of them. So the 3 doesn't mean you have 3 electrons in there. It means you have orbitals that are now 1 part s and 3 parts p when you think about them mathematically. So it occurs when a central atom is surrounded by 4 regions of electron density. So this is showing you again on the left what you add together. You end up with 4 yellow orbitals, which are all 109.5 degrees apart. So for something like carbon, carbon has a 2s2, 2p2 valence electron configuration. And so it would appear like carbon can only form 2 bonds. But if you take one of the electrons out of the 2s and put it into a 2p, and then you add all 4 of those together, you get 4 sp3 hybrid orbitals on the right. Each of them has a single electron in it. So when you think about ethane, ethane is 2 carbons bonded to each other, and then each of those carbons have 3 hydrogens bonded to them. So if you put sp3 hybrids on each of the carbons, then you can bond by overlapping with the s orbital on each hydrogen to form 3 bonds. And then one of the sp3s on each of the carbons can overlap head on head to form another bond. And so you get 7 sigma bonds. So each of those is a sigma bond, because if you cut it across the bond axis, you would see a circle. So 2 other kinds we're going to talk about are hybrid orbitals that use d orbitals. So now we know we're going to have to be beyond neon. You're going to have to be in a level where you have n equals 3 or bigger, because the only time you have d orbitals is when you get up to n equals 3, because d is L equals 2. So in this case, for the sp3d hybrid orbitals, you take an s, 3 p's, and a d orbital. You get 5 new orbitals. We'll call them sp3d. So 1 part s, 3 part p, 1 part d. And they occur when a central atom is surrounded by 5 regions of electron density. So the other type that uses d that we're going to talk about are sp3d2. So you're going to take an s, 3p, 2d, get 6 sp3d2s. And this is going to occur when you need 6 regions of electron density around your central atom. So sulfur will be in the far left, sulfur will be sp3d, because you need 5 regions. The chlorine in the center also needs 5 regions, so that's going to be sp3d. And then the chlorine in the cation on the right also has 5 regions, so it's going to be sp3d. Here is just a picture of the geometry of that on the left, and then on the right, a picture of those orbitals. And it shows you that they all have the right angles that you would expect from VSEPR theory. And then sp2, the same thing. In sp2, we think in VSEPR, what did I say? sp3d2. In this situation, you need regions for 6 pairs of electrons. And all the angles are going to be 90 degrees. So in B, it's showing you that each of those lobes is 90 degrees from the others. So you get that octahedral geometry. And that corresponds to sp3d2. So this is just a picture, a table showing you linear, trigonoplanar, tetrahedral. So linear is going to be sp, trigonoplanar sp2, tetrahedral sp3, trigonal bipyramidal sp3d, and octahedral sp3d2. So the important thing is if you draw the Lewis structure and get the right VSEPR geometry, then all you have to do is look at this table and you can say, this is the kind of hybrid orbitals I have. You don't have to go back and think about why they formed. That was just to help you understand it. But once you know the geometry, you know what hybrid orbitals you're going to need. Okay, so this is showing you that as you go down the periodic table, if you think about it, when you're at the top of the periodic table, the orbitals are pretty small. And so when electrons are in different orbitals, they really want to get far apart. But as you go down the periodic table, so this would be, I think, water and hydrogen, hydrogen sulfide, and then this is selenium, or hydrogen selenium selenide. So this is just going from oxygen to sulfur to selenium down a group. But it shows you that when you're at the top of the periodic table, the electrons are close together because they're in a region of space that's pretty small. But then as you go down and your orbitals get bigger and bigger, then this idea of hybrid orbitals and VSEPR geometry really isn't needed as much, because you can keep, for example, on the far right, it looks like selenium has just its p orbitals overlapping, which would make sense if you didn't have to worry about those electrons getting too close together. So 90 degrees doesn't keep them as far apart as possible. But if they're already far apart because they're in orbitals that are so big, it's not as important. I'm not sure what that example is. And this is just asking you what kind of hybrid orbitals. This would be sp3d, because you need 5 regions of space. And if you have a molecule that has more than one central atom, you could be asked, what's the hybridization on each of the central atoms? So in this case, if we look at the nitrogens, they're the same. They need regions for 4 pairs of electrons. So that means it's going to be tetrahedral or sp3 hybrids on the nitrogens. But the carbon only needs regions for 3. So that's going to be sp2 hybridization. Just another example. Same thing. So the carbon on the left is sp3, the carbon in the middle is sp2, and the oxygen is sp3 because it has 2 lone pairs and 2 shared pairs. So it has 4 pairs of electrons that want to be as far apart as possible. So multiple bonds. So we want to think a little bit more about multiple bonds. And we want to think about pi bonding and the idea of delocalization in resonance structures. So single bonds are formed by the direct overlap of 2 hybrid orbitals, p orbitals or s orbitals. Those are sigma bonds. Our single bonds are formed, and they're called sigma bonds. So all single bonds are sigma bonds. The additional electrons shared in a multiple bond are not a result of hybrid orbitals, but the result of the side-by-side overlap of 2 just normal p atomic orbitals. So if you think back to our process of forming hybrid orbitals, in each case, there was always a p orbital left over in sp2, and then in sp. sp3 doesn't have any leftover, so it won't be able to form multiple bonds. But we're going to be thinking about what can that leftover p orbital on each of those atoms create, what kind of bonding. So a single bond is always a sigma bond. A double bond is 1 sigma bond and 1 pi bond. A triple bond is 1 sigma bond and 2 pi bonds. And so to determine the hybridization in molecules with multiple bonds, we know that a double bond and a triple bond is in the same region of space as, it's all of that electron density has to be in the same region of space. Oops. And so when we look at this, we know that the second bond between the carbons has to also be somewhere between the carbon atoms. You couldn't have it going in different directions. So on those carbon atoms, when we form the sp2 hybrid orbitals, so each carbon needs sp2 hybrids because you have 3 regions of electron density. So each of those sp2 hybrid orbitals can form a sigma bond, 2 of them with hydrogens, and then the third one can overlap with the other carbon. And then notice that we have that p orbital on each of those carbons after you make sp2 hybrid orbitals that still has one electron in it, and it's available to form a bond. And so now when you think about it, you form on the left-hand side, it's showing you that each of the carbons has sp2 hybrid orbitals. 2 of those orbitals will overlap with the s orbitals on the hydrogen to form sigma bonds to the hydrogen. 1 on each of the carbons will overlap with 1 on the other carbon to form a sigma bond between the 2 carbons. But then it shows you that each of those carbons has a p orbital with an electron in it. And so if you squish those 2 nuclei closer together, what you essentially get is an overlap of the red lobe and the blue lobe, and that's the pi bond. So now when you cut that across the bond axis and look at it, the red and the blue are a dumbbell shape rather than a circle, and so we'll call that a pi bond. So the pi bond is formed by the side-by-side overlap of the 2 unhybridized p orbitals on the carbon atoms, and the 2 lobes of the pi bond are above and below the plane of the sigma system. Okay, so now if you have sp hybrids on each of those carbon atoms, remember, if you only used an S and a P, that means there's 2 p orbitals on each of these atoms, carbon atoms that have single electrons in them. And so now they can squish together sideways, and you can form 2 pi bonds. So on the left-hand side, they're trying to show you the yellow is the sp hybrid orbitals. One of those is overlapping with a hydrogen's s orbital to make a sigma bond to hydrogen. The other one is overlapping with a sp hybrid orbital on the other carbon to make a single bond, a sigma bond. But then each of the carbon atoms, so this is acetylene, C2H2, each of those carbon atoms has 2 p orbitals, each with 1 electron. So now when you squish it together, you get a lobe above and below, but then perpendicular to that, because the p orbitals are all perpendicular, you also get a red and a blue lobe. So each of those sets of lobes, a red and a blue, creates a pi bond. So in acetylene, with the triple bond between the carbons, you have a sigma bond formed from sp hybrid orbitals overlapping, and then you get 2 pi bonds from p orbitals on each of the carbons overlapping sideways. So that figure showed the overall outline of the bonds in C2H2. The 2 lobes of each of the pi bonds are positioned across from each other along the line of the sigma bond. So you have the sigma bond, and then you have the pi bonds that were formed this way. So they're going to be 1 pi bond here and then 1 pi bond perpendicular to that, because the p orbitals, you could think that the p orbital that was along the bond axis went into the hybrid orbital, and that creates your bond along the z-axis, for example, and then you'd have the pi bonds in the x plane, axis, and then in the y. So this is a picture where you have sp2 hybrid orbitals in between several carbons, and this molecule is benzene. But notice you can draw 2 resonance structures, so you could just move that double bond. And so that tells us, as we remember from the last chapter, that we don't really have single and double bonds alternating. We have a blend of every carbon has a single bond, but then those double bonds are shared. So each bond is about 1.5 bond orders between the carbon atoms. And so that means that the hybrid is a blend of those 2. And the p electrons are the p orbitals. So the electrons in the pi bonds are not located in one set of p orbitals, which makes sense if you think that those bonds are essentially blended. So really, if you think about it, you have the carbons all bonded in a plane with their sp2 hybrid orbitals. And then each carbon has a pi orbital with one electron in it. So they're all overlapping in that ring to form a big orbital where the electrons can move around the ring. So they're delocalized. They're not held between two carbon atoms. This is just another example, and we'll go through lots of examples of this in class. And I think I'll take a break before I do the last theory, which is molecular orbital theory. We're actually going to do a computer lab on this, so I'll talk about it in these slides, but then after that, we'll talk in class by doing a computer lab, but I think I'll take a break.